the period of an oscillation is the time taken for one complete oscillation. Now, here I have the oscillating object. What is one complete oscillation? The equilibrium position, upper extreme, back to the equilibrium position, lower extreme, and back to the equilibrium position. This is one complete oscillation. The time taken for one complete oscillation is called the period of oscillation. And we generally represent the period by the uppercase T. Do not use the lowercase t for period. Period, the uppercase T of a simple harmonic motion, is the time taken for one complete oscillation. And what is frequency? Frequency is the number of oscillations per second. How many times the object moves up and down. Can you make a guess? How many times is this object moving up and down a second? Well, you can actually measure it. Well, this is about 3 times a second. It oscillates 3 times a second. Means the frequency is 3 per second. 3 oscillations per second. So frequency represented by the lowercase f is the number of oscillations per second, and it is measured in a unit called Hertz, Hz. What does Hertz stand for? It stands for per second, number per second. Alright. Period T and frequency f are related. Can you give me a relation between period and frequency? I just told you that the frequency of this oscillation is 3 Hertz. It oscillates 3 complete oscillations per second. Alright, if it does 3 oscillations per second, what is the time taken for one oscillation? Well, if it does 3 oscillations in 1 second, the time taken for one oscillation will be 1/3 of a second. If it does 5 oscillations in 1 second, the time taken for one oscillation will be 1/5 of a second. Is that right? Okay, now tell me, what is the relation between period and the frequency? One is the reciprocal of the other, or we will have f equal to 1 over t, or t equal to 1 over f. If the period is 2 seconds, if it takes 2 seconds for an object to complete one vibration, then it will only complete half a vibration in 1 second. You see that? If period is 2, the frequency is 1/2. If the frequency is 5, the period is 1/5. You see, one of them is the reciprocal of the other. Frequency is 1 over the period. Alright, let's now go back and get a couple of more important relations. Do you remember the angular frequency omega? What's the definition of angular frequency omega? Omega is theta over t. This is how we define it. Rate at which the angular displacement changes. So omega equal to theta over t. Now tell me, when this t is 1 period, what will be the value of this angle? When the time is 1 period. Now 1 period means, now what is the meaning of 1 period? This is the equilibrium position. Now, when it goes from the equilibrium to the upper extreme, the angle increases from 0 to pi by 2. Now, When it now comes back to the equilibrium position, the angle increases from pi by 2 to pi. And now it goes to the lower extreme, angle increases to 3 pi by 2, comes back to the equilibrium position, the angle is 2 pi. So for one complete oscillation, the angle is 2 pi radians. That means when this time is 1 period, the angle corresponds to 2 pi radians. Therefore, if I replace this angle theta by 2 pi radians, this time will become 1 period. So, what is the value of theta for one complete oscillation? We already answered that. Theta equal to 2 pi for one complete oscillation. Therefore, when theta equal to 2 pi, the time taken for the angle to complete 2 pi radians is called 1 period. So when t equal to uppercase T, if this theta is 2 pi, then this time t will be the period t. Therefore, look at that very important, all-important relationship. Omega equal to 2 pi divided by the period. The angular frequency omega is 2 pi divided by the period. You cannot forget this relation. We will be using it as we go on several times. Alright? Angular frequency omega is 2 pi over the period. Alright. We can also write it as, look at this, 2 pi multiplied by 1 over t, and 1 over t is the frequency. So I can also write it as 2 pi times the frequency. You see, the reciprocal of the period is the frequency. You must know both these relations. Omega, the angular frequency, is 2 pi divided by the period, is the same as 2 pi times the frequency. Alright, now tell me, what is the cause of acceleration of an oscillating object? I showed you this. What is the cause of acceleration? When the spring is pulled down, you can see the spring has now potential energy. The spring is now pulling the object back. Now, the force applied by the spring to get its original position back is called the restoring force. Have you ever experienced the restoring force of a spring? When you pull a spring, the spring pulls you back. You see, it is this restoring force of the spring that provides the acceleration. When the spring is pulled down, the spring wants to restore itself. So that restoring force pulls the object back, and it is that provides the acceleration. So what is the cause of acceleration of a simple harmonic motion? When the ball on the spring is pulled down, the spring applies a force upward to restore its position. You see that? And that force, when the displacement increases, the restoring force F also increases. Is that right? You pull the spring more, the spring will pull you back with a greater force. As the displacement increases, the restoring force also will increase. In the opposite direction, of course. If you pull the spring, the displacement increases downward, the restoring force will be upward. That will be in the opposite direction. When the displacement increases, the restoring force F also increases in the opposite direction. And this can be written as, mathematically, F equal to negative ky. Or we say the restoring force is directly proportional to the displacement, and its direction is opposite to the displacement. That's the negative sign. K is a constant, and we call it the spring constant. You have done this in Physics 1. We talked about Hooke's law. So F, the restoring force on a spring, equal to negative ky, where y is the displacement. Now, it is this restoring force that produces the acceleration. So, if this object has a mass m and the restoring force F is pulling it upward, well, that F will be equal to ma, is that right? Where m is the mass of this object and a is the acceleration. So if m is the mass of the oscillating object, then F equal to ma. So I can replace this F now by ma, and what does the equation now become? The equation now becomes, this F can now be replaced by ma. We have ma equal to negative ky. Alright, can you solve the equation for A? Solving for A, you can have A equal to negative k over m times y. But at the moment, do you remember, I pulled down this step too rapidly. I wanted to ask you, but I hope you haven't read it yet. Do you remember about 15 minutes ago, we derived an equation for acceleration of a simple harmonic motion? Do you remember that equation? Acceleration of a simple harmonic motion. Alright, can you look back? I told you you must remember that equation. Acceleration of a simple harmonic motion is negative omega squared y. A equal to negative omega squared y. So this is the acceleration that we are talking about. So we can replace this A by negative omega squared y. What does the equation now become? M times negative omega squared y. Ma now becomes negative m omega squared y equal to negative ky. And you can see y will cancel from both sides, and you can solve for omega squared. Negative on the left and negative on the right will make it positive. Y and y will cancel. Divide both sides. Well, the simplest way is divide both sides by negative m or negative my. I hope you have followed this. I don't have to do that. Divide by negative my, divide by negative my, and negative m will go, y and y will go, y and y on the right will go. We get omega squared equal to k over m. Beautiful equation. Alright. Now tell me, give me an equation for omega that we have obtained a little while ago. Let's solve for omega from here. If omega squared equal to k over m, then omega equal to square root of k over m. Okay, now let me ask you, what is the equation for omega in terms of the period of a simple harmonic motion? I told you that is something you can never forget. But omega equal to 2 pi divided by the period. So let's replace this omega by 2 pi over t. We can now see 2 pi over the period equal to square root of k over m. Now, what are these things in here? This corresponds to the oscillations of a loaded spring. Well, what does T stands for? T is the period, the time for one oscillation. What does K stands for? K is the spring constant of the spring. What does M stands for? M is the mass of this object. So, we have 2 pi divided by the period equal to square root of